Welcome to the world of EdgeGenix. Today, we are excited to introduce our cutting-edge software solution, Edge Healer, with our project, Self-Healing and Self-Adaptive Management for IoT Edge Computing Infrastructure. In today's rapidly evolving digital landscape, the Internet of Things, or IoT, has revolutionized how we interact with technology. With the advent of Industry 4.0, smart concepts such as smart homes and smart cities have become integral parts of our lives. But as these IoT devices become increasingly prevalent, we face a new set of challenges. One such challenge is the sheer volume of data generated by these devices. With computing in the cloud, there can be latency issues and difficulties in handling massive amounts of data. The traditional approach of relying solely on the cloud for processing and storage is no longer sufficient. This is where edge computing comes into play. Edge computing is a distributed computing model that brings computation and data storage closer to the devices and sensors, generating the data. By processing data at the edge of the network, closer to where it is generated, we can address some of the challenges posed by the cloud. One of the primary benefits of edge computing is reduced latency. Additionally, edge computing helps alleviate the strain on network bandwidth and reduces network congestion. However, edge computing also presents its own set of challenges. Limited resources, including scaling capabilities, computing power, and data accumulation, can hinder the performance and scalability of edge nodes. Reliability is another concern, as the edge infrastructure is prone to failures. Hardware-level failures due to physical conditions can disrupt operations and require significant human intervention. As the number of IoT devices continues to grow exponentially, managing the edge networks becomes increasingly more infeasible and inefficient through manual intervention alone. Diagnostics can be costly and time-consuming, and there is often a shortage of experts skilled in managing large-scale edge deployments. In the ever-expanding realm of IoT-based edge computing, the need for self-healing and self-adaptive management systems has become increasingly evident. While existing research has focused on detecting anomalies at the service container or IoT device level, there is a significant gap in exploring self-healing approaches for faults originating between edge devices and IoT devices themselves. Our project focuses on developing an intelligent management system that can autonomously identify and address faults within the intricate network of edge devices and IoT devices. Once a fault is detected, our system will employ sophisticated self-healing mechanisms to automatically rectify the issue. This is the system architecture of our proposed solution, designed to enhance the functionality and management of IoT edge networks, ensuring improved quality of service, CoS, management and performance optimization. Our software framework comprises several key modules, each playing a vital role in the seamless operation of the IoT edge network. Monitoring agents are deployed on each edge computing node, ECN, and actively capture performance metrics of IoT devices and the network link between ECNs and IoT devices. These performance metrics are then fed into the matrix generator module. Using this information, the matrix generator generates a comprehensive set of metrics, providing a holistic view of the network's health and efficiency. The analyzer module plays a crucial role in detecting anomalies within the IoT edge network. It analyzes the performance metrics and leverages a predefined rule collection to determine appropriate self-healing, or self-adaptive actions. The rule collection serves as a database containing rule-based actions and policies. It can be updated by the user, ensuring flexibility and adaptability to changing network conditions. When violations are detected, the scheduler module comes into play. It migrates the violating IoT services to different ECNs using the Kubernetes API, employing horizontal auto-scaling mechanisms to minimize downtime and optimize resource allocation. To ensure efficient resolution, the configuration and firmware handler modules facilitate configuration updates and firmware management for IoT devices. They identify the most suitable configurations and firmware versions for each fault scenario. The configuration and firmware updater submodules work in conjunction with the relevant handlers at the node level, seamlessly applying configuration updates and firmware upgrades as required. Continuing our exploration of our innovative software framework for IoT edge networks, let's delve into our efficient migration strategy, specifically designed to achieve quality of service requirements through self-adaptation. In our scenario, we consider an IoT camera located in Zone A, with a CoS requirement of 40 milliseconds or below. The latency performance matrix, shown in Fig. 03, represents the latency values between the IoT device and various edge computing nodes in this example. The IoT camera service violates the CoS requirement while connected to node N, as it exhibits a latency of 45 milliseconds. However, nodes M and P, within the same localization zone, demonstrate better latency performance for the IoT camera. To address this violation and optimize the CoS, our migration strategy comes into play. We invoke the scheduler, utilizing the Kubernetes horizontal scaler to initiate the deployment of a new IoT camera service pod on node M. This migration allows the computing task to be seamlessly transferred to node M, which offers improved latency performance within the required threshold. Once the new IoT service pod stabilizes on node M, the old pod connected to node N is removed, ensuring a seamless transition of the computing task. Let's delve into our system's reconfiguration strategy. In our scenario, we focus on an IoT camera connected to an edge computing node where the network bandwidth experiences degradation. This degradation can lead to buffering issues and potential service interruptions in the camera's video stream. To mitigate these challenges, our system employs self-adaptation mechanisms, leveraging the dynamic reconfiguration capabilities of the IoT camera. Key parameters such as resolution, frame rate, and bitrate are dynamically adjusted based on the current network conditions. By dynamically reconfiguring these settings to match the prevailing network conditions, we ensure the uninterrupted delivery of the camera's video stream while maintaining the desired quality of service. This automated reconfiguration capability enhances the overall performance and resilience of the IoT system, providing a seamless user experience even under varying network conditions. To achieve this, our solution incorporates the IoT device's configuration capabilities, enabling it to adapt to the changing network quality through automated reconfiguration. By leveraging these capabilities, our system monitors the network quality in real time and triggers the automated reconfiguration process when degradation is detected. The IoT camera dynamically adjusts its resolution, frame rate, and bitrate to optimize video streaming based on the current network conditions, ensuring uninterrupted service delivery. Let's explore our firmware update strategy. In our scenario, the monitoring agent plays a crucial role. It continually scans and monitors the video feed from the IoT device, detecting any distortion or anomalies caused by corrupted firmware. Upon detecting such issues, our system initiates a self-healing process by triggering an over-the-air OTA firmware update for the affected IoT device. This self-healing mechanism is a significant advancement in addressing firmware-related issues that often require considerable time and effort from IoT system administrators. By automating the firmware update process, our system alleviates the burden on administrators, enabling them to focus on other critical tasks while ensuring the health and stability of the IoT devices. We conducted 2 experiments to evaluate the effectiveness of our software framework in enhancing migration and reconfiguration capabilities in IoT edge computing environments. In Experiment 1, we focused on migration. We looped through a set of images, emulating latency and jitter. We measured the total time taken to correctly identify the set of objects with and without our custom Kubernetes scheduler to simulate different network conditions. We injected latency ranging from 25 milliseconds to 250 milliseconds in 25 millisecond steps. Additionally, we injected latency from 10 milliseconds to 100 milliseconds in 10 millisecond steps. Our metric of interest was the total time needed to identify all objects in the given dataset. In Experiment 2, we focused on reconfiguration. We displayed a 25 FPS video clip while emulating bandwidth limitations. We collected the frames per second (FPS) of the ESP32 camera video output to the IoT service, and evaluated the accuracy of object detection to simulate varying bandwidth conditions. We injected bandwidth limits ranging from 150 kilobits per second to 1150 kilobits per second in 100 kilobits per second steps. Our metrics of interest in Experiment 2 were the frames per second (FPS) of the camera video output and the accuracy of object detection. Now, let's delve into the scheduler performances under the injected latency experiment. By measuring the total time taken to correctly identify the set of objects in the given dataset, we can gain insights into how the scheduler handles both latency and jitter, and manages the processing tasks effectively. As we introduced increasing levels of latency and jitter, We observed their impact on the total time needed to identify all objects in the dataset. The scheduler's ability to adapt and optimize the processing tasks becomes crucial in the face of varying latency and jitter. By comparing the results obtained with and without the custom scheduler, we can assess its effectiveness in mitigating the effects of both latency and jitter, and optimizing the processing time. Let's explore the results of Experiment 2. The experiment results, as shown, highlight the performance improvements achieved through our proposed configuration update approach. In this experiment, we displayed a 25 FPS video clip while emulating bandwidth limitations. We collected the frames per second (FPS) of the ESP32 camera video output to the IoT service and evaluated the accuracy of object detection. The baseline performance without reconfiguration showed a gradual decrease in FPS and object detection accuracy as the bandwidth limit decreased. The system demonstrated significant improvements. By dynamically adjusting the video resolution based on the available bandwidth, the system maintained a higher FPS and achieved improved object detection accuracy. In conclusion, our software framework for IoT edge computing demonstrates its effectiveness in addressing key challenges such as migration, reconfiguration, and network limitations. These advancements contribute to enhanced system performance, efficiency, and resilience in IoT edge computing environments. Together, let us drive the transformation of IoT edge computing and unlock its full potential for a connected and intelligent world.